Welcome to an example of classifications of functions such as one-one function, onto function, bijections, and invertible functions. Check the injectivity and surjectivity of the following function. The function f defined from set of natural numbers to natural numbers given by f of x is equal to x cube. This time, both domain and codomain are given to be set of natural numbers. And image of every element is calculated by the rule x cube, which means image of 2, f of 2 is 2 cube, which is 8. Image of 5 is 5 cube, that is 125, etc. We need to check whether it is a one-one function. What is one-one function? A function f defined from a to b is called one-one function or injective function if distinct elements have distinct images. That is, for any two numbers x1 and x2 which are unequal, their images should also be unequal. Distinct elements imply distinct images. Or, in other words, in case the images happen to be equal for some x1 and x2, then that x1 and x2 should also be equal. So, two interpretations of the definition. First is, when you have two numbers x1 not equal to x2, then their images f of x1 and f of x2 should also be not equal. The second interpretation, in case two images are equal, f of x1 and f of x2 are equal, their pre-images x1 and x2 should also be equal. While checking this example, we can go by either of these interpretations. I'm going by the second one. Let us take two images which are equal for some x1 and x2 of the domain. Let f of x1 be equal to f of x2 for some x1 and x2 of the domain. Which means, what is f of x1? F of x1 is x1 cube. F of x2 is x2 cube. They should be equal. So this equation can be rewritten as x1 cube is equal to x2 cube. Now, don't be casual in taking off this cube sign and write it as x1 equal to x2, which is wrong. The way we should simplify this equation is write it as x1 cube minus x2 cube is equal to 0, a cubic equation. Now, factorize this expression using the identity a cube minus b cube is equal to a minus b into a square plus b square plus ab. Using that identity, we get this left-hand side factorized. x1 minus x2 into x1 square plus x2 square plus x1 x2. The product should be equal to 0. RHS is 0. Now, product of these two factors could be 0 in two ways. Either the first factor equal to 0 or the second factor equal to 0. Now, if the first factor is 0, x1 minus x2 is 0, then x1 is equal to x2. And there is another possibility, this factor could also be 0. So, two possibilities. Either x1 equal to x2, which means x1 minus x2 factor is 0, or this factor is 0. Now, let us check whether this factor could be 0 really. Look, x1 and x2 are two numbers which are natural numbers. Natural numbers are positive numbers only. So, those x1 and x2, their squares will surely be positive numbers. And the product will also be positive number as x1 and x2 both are positive. The sum of three positive numbers can never be equal to 0. There is no negative number. You go on adding positive number plus positive number plus positive number, it will never be 0. So this part, the second part, is not possible for a natural number, for natural numbers x1 and x2. Hence, the only possibility is x1 equal to x2. So, look at this. Whenever the two images are equal, it is compulsory that these two images, these two pre-images should be equal, which is what we wanted to call it a one-one function. Whenever the images are equal, it must imply that the pre-images are equal. Yes, It has strictly implied that if the images happen to be equal, the pre-images would be equal. There is no second possibility to make them equal. This is not possible. Hence, we conclude that this function is well following this definition of one-oneness. Hence, this function is one-one function or injective function. Now, let us check whether this function is an onto function. What is onto function? A function f defined from set A to set B is called onto function or surjective function if for each element y taken in the codomain, there exists at least one x in the domain such that the image of x is the y that you have taken. Which means for every element y taken in the codomain, let us go checking. Let there be a y in the codomain, any y taken from the codomain, first stage. Now we should be able to get an x in the domain corresponding x. How? If possible, let this y taken here be written as x cube. If we want to write this y as an x cube, the x must be y to the power 1 by 3. From this equation, y is equal to x cube means x is equal to 1 by 3. Now we need to check the x that we have calculated. We have got an x. But does it really belong to the domain? The definition says there should exist an x in the domain. Do we have this x in the domain? What is y? Y is any natural number, any natural number. Say for example, I am taking number 3. Suppose y was 3. Then x should be 3 to the power 1 by 3. Cube root of 3 cannot be found in the set of natural numbers. So the x that we are calculating will not belong to the domain. So we started with, if possible, let the y be equal to x cube. Yes, you may write so. But this x that we got is not found in the domain. So if possible, let it be so we started with. Now it has become not possible. X we are getting, but that x may not belong to the domain because, for example, y is equal to 3 if you take, y is equal to 5 if you take, 5 to the power 1 by 3 cannot be a natural number. So the second stage of the definition is being violated. So no point in going checking by the third. Here itself we conclude that this function is not following the onto definition. For a y taken here, we are unable to find an x in the domain, corresponding x in the domain for which we may get the image here. It's not possible. Hence we conclude that this function is not onto function or it is not surjective function. Now, whenever we want to prove that a definition is not valid for an example, it is sufficient to show it through a counter example, a numerical example. Remember, this counter example method is possible only when we want to prove the negation of the statement, when it is not surjective, when it is not onto. So, here we show the same example that we have already considered. Let us take y is equal to 3. And we have already observed that there is no x in the natural number so that x cube could be equal to 3. This numerical example is going against the definition. Therefore, this can be treated as a counter example. So we conclude that the function is not an onto function. Again, once more, remember, to show a statement is not valid, you may go by numerical example, but to show a statement is valid, we cannot go by a numerical example. We cannot go by a counter example.